Hi everyone, this is a continuation of chapter 4a now. The next topic we're going to go through is now more on identifying acids and bases by their chemical formulas. So we talked about acids and bases a little bit leading up to now this topic. Now we're going to go more in depth with it. First, to start out, so some properties of acids. They have a sour taste. We won't be tasting any acids in the lab, but if you're thinking of foods that have a sour taste, like lemons, that is composed of citric acid, for example. Vinegar was mentioned previously too. This is made up of acetic acid. One kind of unique property of acids and bases is how they can cause color changes in plant dyes. Also for acids, they can react with certain metals to produce hydrogen gas. At the very end of part 2, I'll talk a little bit about the reactivity of metals. Not all metals react the same. There's an order of how strongly some metals react or how weak some other metals react. Should be a reaction arrow here. So when magnesium reacts with an acid, it can produce this hydrogen gas. So these bubbles here are hydrogen gas. So H2 gas, we know this is one of our diatomics. It's one of our Brinkelhoffs. Also within acids, they react with carbonates and bicarbonates to produce carbon dioxide gas. Where is carbon dioxide gas in this reaction? Hopefully you recognize it here on the product side. It's a molecular compound, so we name it as carbon. Then there are 2 oxygens, so the prefix di, so carbon dioxide. We change the ending of oxygen to have that ending of IDE. It's our anion here. More specifically, it's our monatomic anion here, so we did need to change the ending to IDE. Here is calcium carbonate. Hopefully you recognize that name as well. And here's carbonate, here's calcium. Carbonate is a polyatomic anion. So for naming this, we just leave the name as is for the polyatomic anions. So we name our cation, calcium, and then we'd recognize this as CO3 2- and Ca2+, where CO3 2- is that polyatomic anion of carbonate. Now, a really crucial property of acids is that aqueous acid solutions conduct electricity. So we talked about electrolytes in part 1. The reason that acids can conduct electricity is because they must have some ions in solution. Specifically for acids, there are these H+ ions. So acids will dissociate into H+ ions and then whatever other component of their molecule when in solution. For example, here HCl, H+ would dissociate from Ci. So H+ would dissociate from Ci. We'll talk more about this dissociation of acids into H+ ions when in solution. Now we're talking about properties of bases. Here's a visual now for this can cause color change in plant dyes. This is true for acids and for bases. It's kind of neat because alkali test, alkali means basic. More specifically though, the alkalinity of something is its resistance to being acidified. So both acids and bases can cause a color change in plant dyes. It can be really pretty, as you see here with these different colors. Then additionally, for properties of bases, they have a bitter taste. They can feel slippery, like many soaps contain bases. So think a soap is definitely slippery. Detergents are slippery. It's likely because they contain a base component. Then, as mentioned, for acids that dissociate into H+ ions in solution, really importantly, bases also conduct electricity. So aqueous base solutions also conduct electricity because of some ion that is present from what we learned in part 1 on electrolytes. The ion that's present for bases in solution is the OH minus ions, which hopefully you're recognizing now based on the formula. This is what we call hydroxide. So that's our polyatomic anion of hydroxide, or OH minus. For acids, we typically just call these hydrogen ions. So hydrogen ions for acids, hydroxide ions for bases. Let's talk more about those ions that are produced for acids and bases in solution. This whole definition is really importantly the Arrhenius definition of acids and bases. So for an Arrhenius acid, which is typically how we think of acids, we'll go into another example of how acids and bases can be defined, but an Arrhenius acid is a substance that produces H+ ions in aqueous solutions. For example, let's say we have hydrochloric acid in aqueous solution. We do produce H+ ions, but maybe you're wondering why then is it represented like this? We'll get into that. So H+ ions and Cl- ions are left over. So HCl can dissociate into H+ ions and chloride anions. And that's because HCl is an acid. So it dissociates into H+ ions. So it's definitely an Arrhenius acid. But then why do we see this H3O+ then? Well, this is when an H+ ion dissociates from an acid. It's in the presence of a water molecule though, so H2O. So H+ from the acid combines with a water molecule to form these hydronium ions, or H3O+. Let me show you that again here on the slide. So that hydronium ion, H3O+, it is important that you're recognizing the name for it as well. So H3O+, hydronium ion. We'll get into molecular shapes a little bit later on in the semester. It has this trigonal pyramidal shape where it has a lone pair of electrons here, and then it has 3 atoms bonded to it. So you may be able to start imagining this kind of looks like a pyramid, at least in 3D space. So when we start to draw out molecules in 3D space, we're going to start to assign some shapes to them, but we'll get there later in the semester. A hydronium ion, similar to a water molecule, does have this area of partial negative charge, if you remember from part 1, and partial positive charge, where the partial negative charge is still in the area of the oxygen. So here is H3O+, so all of these are H's, and this is oxygen. Then a partial positive end on the hydrogen atoms. You definitely do not need to understand this reaction scheme or worry about it. I just wanted to show you in general how we can go from a water molecule. We add an H+ that came from an acid dissociating. Then H+ with H2O leads to this hydronium ion. What we'll end up seeing as well is that a water molecule can also dissociate into OH-. So what would that mean about water? Well, this means that water can act as a base as well as an acid. So a water molecule can actually dissociate into H+ ions. That H+ ion can combine with another water molecule that's in solution to form these hydronium ions. On the other side of this, the water molecule can dissociate into OH- ions, or hydroxide ions, which we just learned is the definition of an Arrhenius base. So let's go back to that slide now. So we recognize HCl as an acid. It dissociates into H+ and Cl- in the presence of water. Then an H+ ion combined with H2O to form hydronium. Then we're left with just Cl-. Now for an Arrhenius base, so here it can produce OH- ions in solution. It depends on some other factors, but water can be both an Arrhenius acid and as an Arrhenius base. So water can act as both a base and an acid, and you'll see this more in chapter 4. So technically, Arrhenius Base is a substance that produces those OH- ions in aqueous solution. Here we have a water molecule. Here we have ammonia. Now on this side of the reaction, we have hydroxide anions, and then do you remember what this is called? NH4+. This is an ammonium cation, right? An ammonium polyatomic cation. This here, not to be confused with ammonium, this is ammonia. This is an ammonium cation. So let's see what happened here. It looks like ammonia, NH3, accepted a proton from H2O. That led to an increase in hydroxide anions on the product side. So overall, this is a base reaction because OH- ions are present now on the product side. So what ended up happening here is that ammonia, NH3, it took on that other hydrogen from water to become the ammonium cation of NH4+. So altogether, we still have the same number of atoms on both sides, right? We have NH3, so NH4, that means we need to account for one more H. Here's OH. This all together does add up to H2O. So here we do have H2O and NH3 on both sides. Just here it's in water and ammonia. Here it's in the form of an ammonium cation and a hydroxide anion. Again, these are all definitions that are considered Arrhenius acids and bases. So they either dissociate H+ to form H3O+ hydronium ions for Arrhenius acids, whereas Arrhenius bases will produce those hydroxide or OH- ions in an aqueous solution. This Arrhenius definition is typically how we think about acids and bases, so producing H+ or OH- ions in solution. Then this should be a review. So we know for denoting states of matter, we can have solid, liquid, and gas. And then we've also looked a lot now at that aqueous or water-based solution. So for example, hydrochloric acid in aqueous solution is going to dissociate into H+ and Cl- that are also both in aqueous solution. They're still in that water that the original HCl was in as well. Notice when HCl gets dissolved into liquid water, we had an H+ and Cl- ions formed. Cl- is still here. H+ then, we know, combined with water right now to form H3O+, or those hydronium ions. Okay, so keep in mind these states of matter and how we denote all these. For acids and bases, we're mostly thinking about what's dissolved in water. So you'll see a lot of that aqueous here for the state of matter. This is table 2.5 in your book. So here are some simple acids to be aware of. We remember that an acid can be defined as a substance that yields hydrogen ions when dissolved in water. This is technically our Arrhenius definition of an acid. So if we know this definition to be true, then for each of the acids listed, we should recognize that there is one ionizable hydrogen. So there is H, 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 H here. So this has at least one hydrogen that can dissociate. When that acid dissociates and it produces those H+ ions in solution, then we can also link these to our corresponding anions. So for the corresponding anion, for example, let's look at HBr. We know that can produce H+ ions. Then what's left is our Br-. Where did we get that from? Well, H+ has a +1 charge. This whole molecule is neutral before the H+ dissociates. So Br has to have a -1 charge to make this whole molecule neutral. So if this is neutral and H has a +1, Br has to have a -1, We also know this to be true because Br- is a halogen, or bromine is a halogen, so it will form those -1 ions as a halogen. So the corresponding anions, you can see we have F-, Cl-, Br-, and I-. For cyanide as well, Cn-, overall -1 charge, right, for that polyatomic anion of cyanide. For hydrosulfuric acid, if this dissociates into 2H+, then each one of the hydrogens is +1, and overall, we know that this needs then to be 2-. We also know sulfur, it's placed on the periodic table, where sulfur prefers to form these 2- ions, which we call sulfide ions. We took sulfur, and we changed the ending to IDE, so sulfide. Okay, so we can match up the acid with its corresponding anion. We notice that it has a charge here because the H+ is dissociated, because all of these are examples of acids. So that was table 2.5. We have table 4.3 as well. Similar to strong and weak electrolytes and how they either fully dissociate into ions or they partially dissociate into ions, we have strong acids and weak acids as well. Where strong acids, we can recognize, have these memorized, it's HCl, HBr, HI, and then these, as a strong acid, these will fully dissociate into their respective ions. Well, what about this example? From what we learned in part 1 of chapter 4, if we have 2H+ that dissociate, will this portion of the acid also dissociate? So we recognize this as a sulfate anion, SO4 2-. This is a molecular ion, so this will not dissociate further. So H+ will dissociate, but again, this polyatomic anion, that will not further dissociate. So this was brought up in part 1. Okay, same for these polyatomic anions as well. The H+ can dissociate, but not the polyatomic ion form of nitrate, for example. So strong acids will fully dissociate into their ions, but we keep in mind that the polyatomic form, that polyatomic portion of the molecule, will not further dissociate. But the H+s will fully dissociate because these are strong acids. So what about these weak acids? If they do not fully dissociate, it means that their H+ and counter ion, they do not fully dissociate. What might this look like then? Let's look at nitrous acid as a weak acid example. We have HNO2. So remember, this is nitrite. So NO2-, that's nitrite. This is the polyatomic anion counterpart to our hydrogen that will partially dissociate because this whole thing is a weak acid. What this is going to look like then in aqueous form, we'll have H+ in aqueous, we'll have nitrite, NO2- in aqueous, but again, because this is a weak acid, it does not fully dissociate, then we will still have some of this original acid present in solution. So it doesn't fully dissociate. We're still going to have some of this full weak acid present on the product side. If you go on to take organic chemistry, which I hope some of you do, you'll get more into why these are strong acids and weak acids. For our purposes, it's best to memorize or have these written on your note card that these are strong acids, examples of strong acids. These are examples of our weak acids, and then to connect what that means, if this is a strong acid versus a weak acid, where strong acids will fully dissociate into H+ and their counter ions. And if their counter ion is a polyatomic ion, we know that doesn't dissociate because that's the molecular portion of the acid. Then for weak acids, these will not fully dissociate into H+ and their counter ion, So we'll still have H+, the counter ion, but then some of this original acid present on the product side. Now for Arrhenius bases, we did talk about the fact that bases are substances that yield these hydroxide ions when dissolved in water. Let's take a look at some examples here. So sodium hydroxide will yield Na+ and hydroxide ions in water. Potassium hydroxide will also yield K+, now this is potassium versus sodium, and OH- ions in solution. Another example of a strong base, so these are all strong bases. So another example of a strong base is barium hydroxide. This will yield Ba2+ and OH- ions in solution. So for a strong base, similar to what we saw for a strong acid, these will fully dissociate into hydroxide ions and the counter ions in solution. What do you recognize about Na+, K+, and Ba2+? Or I suppose, what do you recognize in the actual chemical formulas? What do you recognize about sodium, potassium, and barium? These are either alkali metals or alkaline earth metals. When an alkali metal in group 1A or an alkaline earth metal in group 2A is in an ionic compound with OH- or hydroxide, they're going to yield strong bases. So sodium hydroxide, we recognize this as a group 1 element. It could also be a group 2 element that does lead to a strong base, where this strong base fully dissociates into Na+ and OH-. This also applies for other alkali and alkaline earth metals on the periodic table. We can have calcium hydroxide, magnesium hydroxide, lithium hydroxide. So any of these group 1A or group 2A metals listed here. So we just went through Arrhenius acids and Arrhenius bases. They had a very specific definition where Arrhenius acids will dissociate into H+ ions in solution. Arrhenius bases dissociate into OH- ions in solution. Now we have another definition of how we can describe acids and bases. These are called Bronsted acids and bases, and their definition is a little bit different. So a Bronsted acid is defined as a substance that is a proton donor. A Bronsted base is defined as a substance that is a proton acceptor. Nothing to do with OH- ions, just the fact that Bronsted acids donate protons, Bronsted bases then accept protons. What does this look like then? Let's say we have ammonia and then we have water. Let's figure out what's a Bronsted acid and what's the Bronsted base here. For a Bronsted acid, we need to see that it donated a proton when we go from reactants to products. Here on the reactant side, we have H2O for water. We notice on the product side, though, it's just OH-. That means that H2O must have donated a proton to then be left with just OH-. Because this water molecule donated a proton, then this water molecule is a Bronsted acid. For ammonia, it has to accept a proton. It went from NH3+. So NH3+, it accepted this proton. It started at NH3. It accepted this proton from water, that's our Bronsted acid here, to then become NH4+, because it accepted that proton. So we can kind of think of it on the reactant side. So H+ is a reactant from the water. That's what gave it this H+. So H+ plus NH3 yields this ammonium ion. So here's our Bronsted base, ammonia. It accepted a proton. Here's our Bronsted acid or water. it donated a proton. Again, for Bronstead, we're no longer thinking in reference to these OH- or hydroxide ions, just in relation to whether something donates a proton or accepts a proton. Now, you may be wondering about these labels here, so let's talk about those. So NH3, or ammonia, reversibly reacts with water to produce ammonium and hydroxide ions. Because ammonia accepted a proton, it's a Bronsted base. Because water donates a proton, it's a Bronsted acid. Now this double-headed arrow, this implies that the reaction is reversible. For the reaction to be reversible, it means we can go the forward direction and the backwards direction. For the backwards direction, why is this now an acid and why is this now a base? So the ammonium cation is now considered an acid when moving this direction for the reaction. It's a Bronsted acid because it ends up donating one of its protons to become NH3+. So here on the product side, ammonium cation is a Bronsted acid. Then for this hydroxide ion, why is this a Bronsted base? Well, it's OH-. It then ends up being water on this side, so it accepted a proton. So here OH- on the product side is a Bronsted base. Something that's helpful in identifying Bronsted acids and bases is to find the original reactant, then match it up with its product. Then see what's the difference on the reactant side versus the product side. Well, this definitely gained a proton or it accepted a proton, so we call this reactant a base because it ends up accepting that proton. For water, we find its sort of matching pair over here. It went from H2O to OH-. Then if this lost a proton or it donated a proton, then this reactant here of water is a Bronsted acid. So for both Arrhenius acids and Bronsted acids, they both must contain at least one ionizable proton, right? It needs to be able to dissociate from its molecule. So H2O does have one ionizable proton to then become H+ and OH-. One of these protons has to be able to dissociate from its molecule for it to even possibly be a Bronsted acid or an Arrhenius acid. So now that we've gone through Bronsted bases on the last slide, let's come back to this first example comparing Arrhenius versus Bronsted bases. We know ammonia is our Bronsted base because it accepts a proton here to become NH4+. Water is our Bronsted acid because it ends up donating a proton. Now going back to the Arrhenius definition, where a base will lead to the production of OH- ions in solution, the ammonia here is actually also our Arrhenius base because it reacts with water and ends up leading to a dissolution or a production of OH- ions on the product side. Here though, I mentioned that water can act as both an acid and a base, so let's take a look at this. So here in this top reaction, water reacts with hydrochloric acid, so it ends up accepting a proton to become H3O+. So here water is acting as a base because it accepts a proton. In the bottom reaction, however, the one we've been looking at with ammonia, here it donates a proton to ammonia, so ammonia becomes NH4+, then water is left just to be OH-. So here in this bottom reaction, water acts as an acid. In the bottom right figure, you can see two water molecules reacting together, where one can act as an acid and the other can act as a base. So one can donate a proton and one can accept a proton. We call water an amphoteric substance because it can act as either an acid or a base, depending on the environment that the water molecule is in. Now, within the category of acids, we can have monoprotic and diprotic acids. So mono being one, protic meaning a proton. So we call this a proton. Why might this be called a proton? Well, we have hydrogen. It has an atomic mass of 1 and an atomic number of 1. From one of your post-lab questions, post-lab assignments, we know that hydrogen contains only 1 proton and 1 electron and no neutrons. So 1 proton, 1 electron, no neutrons, so positively charged, negatively charged, or neutral, respectively. Then for hydrogen to become a cation, it means it lost 1 or more electrons. Hydrogen only has 1 electron to lose. When hydrogen loses that electron, it becomes H+. What's left then for H+? Just 1 proton. So H+, we end up calling just a proton. Okay, so H+, we end up calling a proton. You'll see this show up again and again. Because what is H+ at this point as a cation? Well, it is just then 1 proton. So this difference between a monoprotic, and diprotic, di being 2, is the number of, quote, ionizable H atoms or protons. For example, HCl, it has this 1 hydrogen, which can then dissociate for 1 proton. This is a monoprotic acid because it only has 1 hydrogen here to be ionizable. Here we have 1 hydrogen again, so it can dissociate. It's still an acid, but it's a monoprotic acid because it can dissociate and produce 1 hydrogen ion in solution or 1 proton. Because this is a strong acid, this is a strong acid, these are strong electrolytes because they're strong acids and they completely dissociate into their respective ions in solution. These are strong electrolytes, strong acids, and also considered monoprotic acids. Then for acetic acid, we've seen this will dissociate into H+ and its counterpart, but very importantly, as a weak acid, will also have the original acid fully intact on the product side. Because it does not fully dissociate, this is considered a weak electrolyte and a weak acid. So weak acids are weak electrolytes, strong acids are strong electrolytes. Same with bases as well. Weak bases are weak electrolytes, strong bases are strong electrolytes. So acetic acid is a weak acid, a weak electrolyte. It does not fully dissociate. What it also is then, it's a monoprotic acid because this is the only hydrogen that can be ionizable. Don't worry about this too much at this point, but this portion of the molecule, CH3, these protons cannot dissociate from carbon. This hydrogen here can dissociate from oxygen. This is the only ionizable proton in acetic acid, making this a monoprotic acid. Now for diprotic acids, we can still have strong acids and weak acids. We can even have one molecule be both a strong acid and a weak acid, depending on its ionization state. For example, here's sulfuric acid. This is a strong acid. So going back to our table here is sulfuric acid. It's definitely a strong acid. But notice that it's a strong acid as H2SO4. So let me go back to this slide. So H2SO4 is a diprotic acid altogether because it can technically dissociate 2 hydrogen atoms or 2 protons, we can say now. So when the first proton dissociates, we still have 1 proton remaining. And we have no H2SO4 fully intact on the product side. So this fully dissociates into H plus and HSO4 minus ions. There's one more ionizable proton here though, so now we can put this molecule here. It will further dissociate into H plus and then SO4 2 minus. Technically, as a weak electrolyte, we'll still have some of this HSO4 minus here on the product side. Also notice whenever an H plus is dissociated, we have the other counter ion be a minus, 1 minus. So here's HSO4 minus. When this dissociates into another proton, this charge here becomes 2 minus now, because now 2 protons are missing. The diprotic acid here is the fully intact H2SO4. This is a version of H2SO4, but it only has one more ionizable proton remaining. Now, interestingly, when H2SO4 dissociates into H plus and HSO4 minus, it does so completely. So it fully dissociates into those ions, meaning this is a strong electrolyte and a strong acid. However, when we have just HSO4 minus, and it can also dissociate into another proton, this form of the acid is actually a weak form of the acid. It does not fully dissociate, so we will have some of this original form of the molecule present on the product side. So what's the gist here? Well, monoprotic acids have one ionizable hydrogen or proton, meaning they have one proton that can dissociate from the molecule. Diprotic acids, they have two ionizable hydrogens that can dissociate from the molecule. Now you may be wondering, is there an additional step to this? Yes, some acids are actually triprotic acids, where they have 3 ionizable hydrogens or 3 ionizable protons. So H3PO4 we're looking at on that slide. Phosphoric acid is technically a weak acid. So it's triprotic, but it's a weak acid. So technically, we will have some of this original H3PO4 present on the product side because it's a weak electrolyte, a weak acid. It does not fully dissociate. So it's a weak electrolyte, weak acid. We're going to have some of this original molecule here on the product side. Then this form of the acid can go on to further dissociate. So we have H plus and HPO4 2 minus. Notice the increase in minus charge here. Then HPO4 2 minus can further dissociate a proton, and this is a typo that I will fix. This should be PO4 3 minus. So that's an important typo I'll fix, so sorry about that. Technically, these are all weak electrolytes. They don't fully dissociate into their ions. So really, we could have some of this original acid here even present on this side of the products. Okay, so this will not fully dissociate, this will not fully dissociate, this will not either. So we'll sort of have the presence of all these different options in solution for a weak electrolyte and a triprotic acid like this. To connect the formula to the name to start getting you comfortable with this, H3PO4 is phosphoric acid. You may recognize this PO4 3 minus as phosphate. So the name of this, because it's an acid, we call this phosphoric acid. So we change the phosphate to have that IC ending, and then we add acid. So for these triprotic acids, they have 3 ionizable or 3 hydrogen atoms or 3 protons that can dissociate from the molecule. So here's 1, 2, 3. This is called a triprotic acid. Given that background, let's go through and classify each of these as either ionic, molecular, an acid, and a base. Distinguishing ionic versus molecular, that will be good practice from what we've looked at prior, but now we have possibly an acid or a base included in here as well. So to solve this, it's going to be really important to find from the chemical formula, can we identify, is it a molecular compound or an ionic compound? Is it an acid? Is it a base? We know from chapter 2 that ionic compounds are made of both a metal and a nonmetal, whereas molecular compounds are made from all nonmetals. So some review of acids. Now we're focusing, I should mention, on the Arrhenius definitions of acids and bases. So can they lead to the production of H plus in solution, or can they lead to the production of OH minus in solution? So here's our acids, and here's our bases. So acids are molecular compounds. They're molecular that can release H plus cations when dissolved in water. For example, we've seen hydrochloric acid here. Technically, if we're naming this molecular compound, it's two nonmetals, so we'd name it hydrogen chloride. Hydrogen chloride as a gas, we should name it as hydrogen chloride. So molecular compound, we change that ending to IDE. However, if HCl is dissolved in water, we can actually call it by its acidic name, so hydrochloric acid. We dropped the ending of IDE, we changed it to IC, and we added that word acid. So as soon as it dissolves in water, it will release cations, H+, and leave the counter ion of Cl-. We've talked about these hydrogens now as being ionizable hydrogens or ionizable protons. Another way to think of these hydrogens is that they're acidic hydrogens. So they're usually listed first in the chemical formula. So that will help us start to identify what's an acid, what's a base. So this hydrogen is listed first. Conversely, compounds which are not acids do not usually have their hydrogens listed first in their chemical formulas. An exception to this, or a few exceptions, water does have hydrogen listed first. Hydrogen peroxide, which you may use at home. So hydrogen peroxide is H2O2, 1 hydrogen per 1 oxygen, or hydrogen per oxide. So the two exceptions here is we have hydrogen listed first, but these are not usually called acids. We have seen that water can act as an acid. So technically, water can act as an acid depending on the solution it's in, so it could donate a proton. We don't really call water as being an acidic solution. So hydrochloric acid, though, aqueous form will dissociate into H+ and Cl-. This is our acidic hydrogen, or its ionizable proton is here. So this proton is ionizable. When it dissociates then, dissociates into these H+ ions or protons. So here's our acidic hydrogen or ionizable proton. And then here's our proton on the product side. To be balanced, we have to include this anion here as well, so chloride. For strong bases, we've looked at this too, so it's a good refresher. Strong bases now are ionic compounds. So remember we looked at those bases in group 1 and group 2. So these are ionic compounds which release hydroxide anions when dissolved in water. For example, sodium hydroxide. Sodium we know is in group 1. The sodium hydroxide is a strong base because it fully dissociates into ions of sodium plus and OH minus or hydroxide anions. Other examples of strong bases that we know could be barium hydroxide, where barium is in group 2. So strong bases are ionic compounds, meaning they contain a metal and nonmetal, where the nonmetal component is OH minus. They're strong bases. They're also, we know, strong electrolytes. So strong bases, strong electrolytes, they fully dissociate into solution we can recognize a strong base by this metal here being either from group 1 or group 2. Generally for strong bases, we think of this metal being from group 1 or group 2. Let's go through the first two now. So KF and then NaClO3. For KF, potassium is definitely a metal, fluorine is definitely a nonmetal. So right away, just from the formula, we can say that KF, or potassium fluoride, is an ionic compound. Is this a base? Is this an acid? Well, does it contain H or OH minus that could potentially dissociate from this molecule? No, right? It doesn't contain H or OH, so this is neither a base nor an acid. Okay, so it's definitely ionic, and that's all we would check off here. Here we have sodium that we know likes to form Na+ ions. Here's chlorate that we have memorized, or we have ability to access this ion name quickly, so sodium and chlorate. We do know it's an ionic compound. Here's our metal. Here's our polyatomic ion, where this is all non-metals. So it is ionic, but does it contain H or OH minus that could dissociate from this molecule? No, right? It just has Na, Cl, and oxygen. So going back here, this is ionic, but again, that's all we would check off here. Next, let's look at these two. So from the formula, these start with H. So that's a pretty big hint that we may be dealing with acids. So H2SO3, acids are molecular compounds. Going back here, an important connection to make is that acids are molecular compounds that can release H+ cations when dissolved in water. Then for bases, strong bases, these are ionic compounds now, which release OH- ions when dissolved in water. So really importantly, acids are molecular compounds that can release H+ cations when they dissolve in water. Strong bases are ionic compounds which release OH- ions when dissolved in water. So because this starts with H, starts with a hydrogen, we can probably derive the conclusion that this is an acid, and specifically, we could say this is probably a diprotic acid because it has these two ionizable hydrogens or two acidic protons. We know acids are probably molecular compounds. To further prove this, to show it's a molecular compound, are any of these metals? These are all non-metals, right? So this is a molecular compound. Next, for HF, this does start with an H, and it's not one of our exceptions of water or hydrogen peroxide, where these, though they start with an H, we don't technically usually classify them as acids. So this starts with an H, and it's not one of our exceptions. So this is an acid. We probably also recognize this as hydrofluoric acid, one of our weak acids. Weak doesn't mean it's not dangerous, by the way, right? So in Breaking Bad, they use hydrofluoric acid to dissociate and dissolve the calcium that's in bones. So it's definitely a dangerous acid to work with. It can be extremely harmful to human skin and bones. How we define that weak acid, though, not as far as danger, but it does not fully dissociate into ions. So it doesn't fully dissociate into H+ and F-. We're going to have some HF also present. On the product side of this reaction, that's the only reason we call this a weak acid. It does not fully dissociate into H+ and its counter ion. Instead, there's going to be some non-dissociated HF present on the product side that doesn't get dissociated. Don't take this name, though, to mean that it's a perfectly safe acid. It's a weak acid. It is a weak acid, but it's also very dangerous. Coming up here to show you, this is a weak acid. One to remember, or one to memorize. It's a little bit maybe unexpected because these halogens are considered strong acids when with hydrogen. HF, though, is a weak acid. Then we decide, is it molecular, is it ionic? Then to further prove this, are H or F, are they nonmetals? Yes, both hydrogen and fluorine are nonmetals, so this is definitely a molecular compound. To differentiate, is it monoprotic, diprotic, triprotic? It only has one hydrogen here, so this is a monoprotic acid. So monoprotic here, diprotic here. Right, so these two hydrogens, but then just one hydrogen, so diprotic and monoprotic. That means our final table should look like this. We know we checked off just ionic for these two. These are molecular and they're acids. I'm going to go through one example from the main slide deck, just part of example 4.3. For more examples of this, be sure to check the full solution for example 4.3 in the main slide deck. In 4.3, we're classifying Bronstead acids and bases. Importantly, this is different than Arrhenius acids and bases, right? There's different definitions. For Bronsted acids, it's defined only as the fact that it can donate a proton, or it does donate a proton. Bronsted bases, they're defined as proton acceptors here. Here in 4.3c, we're going to talk through together. So we're going to classify this as either a Bronsted acid or a base. In solving a problem like this, we should think, what are the characteristics of a Bronsted acid? Does it contain at least one hydrogen atom that can then be donated? Well, yes, it does. Then for Bronsted bases, you'll encounter most of these Bronsted bases are anions. If they can accept a proton that has a plus or a positive charge to it, then Bronsted bases have a negative charge to it, typically. So H plus with an anion, this technically can be considered a Bronsted base. So we need to decide if this anion, right, this is also an anion and it has this hydrogen, could that also accept a hydrogen to then be considered a Bronsted base? Well, the answer here is that this bicarbonate ion can actually act as both a Bronsted acid and as a Bronsted base. For it to be a Bronsted acid, it has to be able to donate a proton. So here it starts out as HCO3 minus. It donates a proton. And here we have CO3. This should be 2 minus. So I'll fix that in your slides. Notice this has a -1 charge. When it dissociates into a proton with a plus charge, this sign gets further negative. So this is 2 minus. This bicarbonate ion then is technically a Bronsted acid. Then why is it also a Bronsted base? Well, if we go the other direction and think about it accepting a proton to form carbonic acid, it can do that. So here's HCO3 minus, it accepts a proton, then it becomes this full form of the acid that's diprotic. So here's our diprotic acid that we started with. It can dissociate one proton to form this species. This can further dissociate to produce another proton and this species. So this can accept a proton as a Bronsted base. This can donate a proton as a Bronsted acid. When thinking about accepting or donating a proton, one way that I recommend thinking about it is from the reactant side to the product side. Is a proton being donated from the reactant side to the product side? Yes, right? So this is donating a proton. Starting on the reactant side, it donates a proton that we see then on the product side. What about this base accepting a proton? So here on the reactant side, it's this ion. When it accepts a proton over here, it then becomes this form of the species on the product side. So this went from this form of the species to accepting a proton, which we then see on the product side. This is a definition you might see in your book, so just something to note. This HCO3- species is considered amphoteric because it possesses both an acidic and basic properties. It has both acidic and basic properties. So amphi meaning both. Amphi meaning both, like an amphibian can be on both land and in water, so it can live in both land and water as an amphibian. So amphoteric, it can possess both acidic and basic properties. So if you see that word, that's where that comes from. The next topic now is predicting the products of a neutralization reaction. So now that we've gone into a lot of acids and bases, when an acid is combined with a base, it can result in a neutralization reaction. Let's take a look at strong bases and strong acids first. We know that both strong bases and strong acids are both strong electrolytes. They can completely dissociate into their respective ions. When a strong acid and a strong base, like hydrochloric acid and sodium hydroxide, react together in a neutralization reaction, they'll form a salt and water. So you think of salts as these ionic compounds, so Na and Cl. So Na and Cl come together to form this salt. Then from our strong acid, H will be donated. From our strong base, OH will be donated. These come together from the strong acid and strong base to then form our water. What's remaining from the reactant side to the product side then is that salt. To think about the net ionic equation for this neutralization reaction, we can write these out into their respective ions. So H plus and Cl minus, Na plus and OH minus, then here Na plus and Cl minus, keeping just water. So because water is in its liquid form technically here, we don't write out its ions. So what we think about is this canceling out here, Cl minus here, leaving just H plus from the strong acid, OH minus from the strong base, combining together to form water. So for a neutralization reaction, strong acid and a strong base, think about them forming this salt from this cation of the base and this anion of the acid. Then what's left over then is H2O. What about weak acids and weak bases that are weak electrolytes, so they do not fully dissociate into solution? They do not fully dissociate in solution. So here we have hydrogen and cyanide, here we have sodium hydroxide. This is still a strong base. So for this example, we're just looking at a weak acid, but with a strong base. Let's see what happens then. We have HCN. Then to write out the ionic equation, because this is a weak acid, it does not fully dissociate in solution. So we can really think of this as HCN still intact. Then Na and OH as a strong base does fully dissociate into Na plus and OH minus. Then on this side, we have our salt, right? Because a weak acid and a base will form salt and water. So this breaks up into Na plus and Cn minus and water. then this should not be crossed out here, so this still remains. The only ion that we will cancel out is Na plus and Na plus. Then we're left with HCN, our weak acid, OH minus, CN minus, and H2O. The important takeaway is to note for a neutralization reaction, we're going to take an acid and a base, be it a strong acid and a strong base, or a weak acid and a strong base, or a weak base and a strong acid. These are going to yield salt and water. A weak base and a weak acid will also yield a salt and water, but the reactions get a little bit more complicated. Now, this is the general takeaway that's important, so yields a salt and water. There is another scenario that can happen where the acid and the base yield a salt and water still, along with carbon dioxide. I do want to point out why this is a salt as well before moving on fully. So this is Na+, our metal. Cyanide is our nonmetal. This is an ionic compound, where for the ionic compound, it's just a fancy word really for a salt. So this is our salt, and here's water, weak acid, and strong base. So now some neutralization reactions can produce a gas, so carbon dioxide. So here we have our salt and water, as well as carbon dioxide on our product side. This should be noted as a gas. So this can happen with acids and bases. No matter what we're doing here though, we're still gonna form a salt and water with the addition of an acid with a base. We're also always going to have a balanced reaction. That's not specific to acid and base reactions, but we're always gonna have a balanced overall reaction. So just in general, we're always gonna make sure we have a balanced overall reaction. So here's our acid, here's our base, here's our salt, water, carbon dioxide. To write this out as a net ionic equation, this breaks up into H plus and Cl minus. Importantly, we're matching the molar coefficients here. Sodium, here's 2, carbonate, CO3 2 minus. It basically has this implied subscript of 1, so we have a 1 out here. That's implied. Then sodium and chloride, we do carry on that molar coefficient here, water, carbon dioxide. So what ends up canceling out is 2 Na plus, 2 Cl minus. Then we have just protons, carbonate ions, water, and carbon dioxide. Notice this is the net ionic equation. That's why we don't have this inclusion of the salt, because the salt ions end up being spectator ions. But when this original reaction happened, we did form salt, water, and carbon dioxide. Here in the net ionic equation, we're not going to see that salt because it's composed of the spectator ions that are involved, and they appear on both sides of the reaction in the same form. Okay, let's put all of that into practice now. So let's predict the products of this reaction below. We might notice this looks like an acid. This is sodium hydroxide. We're starting to recognize as a base. So we're going to complete the right-hand side of the chemical equation. And as always with any of these kinds of problems, we're going to make sure our reaction equation is balanced. So from memorizing these and or having them written on your note card, HBr is a strong acid, sodium hydroxide is a strong base. HBr is an acid. We can see that because it starts with an H. This should give us a strong hint that this is an acid. So from its chemical formula, it starts with an H. It's not water, it's not ammonia, so we can get a hint that this is probably an acid. So for the acidic hydrogens in a simple acid, they're usually listed first in the chemical formula. Sodium hydroxide, it's either a group 1 or group 2 metal with OH minus. So this is a strong base. It's made up of Na plus cations and OH minus anions. It's also an ionic compound. because here is our metal and here is our nonmetal. And so all together they're in this form of NaOH. A big hint with those strong bases is to remember that a metal, either in the group 1 or group 2 on the periodic table, paired with hydroxide are going to be strong bases. Here, sodium is in group 1 and it forms +1 cations. This is table 4.3 that, again, you'll have memorized or get used to seeing these formulas or have it written on your note card. So HBr here shows up. This is called Hypobromic acid. This is a strong acid. So because we know they are strong acids and strong bases, now that we know the strength, we can start to associate that this will dissociate into H+ and Br-. This will dissociate then fully into Na+ and OH-. We know on this side we're going to need salt and water. Here's where the water will come from. So the H+ from the strong acid and the OH- from the strong base. That means for our salt, we need to put these ions together. We always list cation first, right? Always, always, then the anion. So the cation here is Na+. The anion here is Br-. Doing the cross method of sorts, we have Na1 and Br1. That simplifies to just NaBr. So NaBr here and with water. Now we need to also check that our equation is balanced. So we know in our neutralization reaction, we're going to form always a water and salt. So always water and a salt. So we wrote this out. Here's our salt listed as the cation first, then the anion, then water. Is this a balanced reaction? Let's see. There's one Na and one Na. There's one Br and one Br. There's one hydrogen, two hydrogens on the reactant side. There's two hydrogens on the product side. There's one oxygen and one oxygen. So this equation is balanced as is. Here's our salt, here's our water, here's our strong acid, here's our strong base. So acid, base, salt, and water. This looks good. We did make sure it's balanced. So to better visualize these neutralization reactions, it may be helpful to rewrite the molecular chemical equation instead now as an ionic equation. So for HBr, this will dissociate like we saw into H+ and Br-. We know when this is in an aqueous solution that water molecules will also be present. When we have a water molecule and one of those acidic protons now in solution, H2O and H+ will form our hydronium ions that we talked about towards the beginning. So HBr will dissociate then into H3O+ and Br-. Sodium hydroxide will dissociate into Na+ and OH-. Here still is our salt and water. Notice that because we added one of these water molecules here that was maybe kind of floating around in solution that combined with H+, we needed to add a 2 here to keep this balanced. So we added this imaginary kind of water molecule. So H+ went on to form H3O+. That means we needed another water molecule here on the product side. So now we have all of our reactants written out truly as their ions, including denoting H+ combining with water to form hydronium now. Then on the product side, we do know our salt will dissociate into Na+ and Br-. We leave our water as is. Now, in writing out those net ionic equations like we did in part 1, the important part here now is to cancel out any of our spectator ions that show up in the same form on both sides of the equation. So Br minus, Br minus, Na plus, Na plus. Now we just have hydronium, hydroxide yields 2 water molecules. These 2 water molecules are neutral. What's important to see here is regardless of the initial reaction we came to work with, so regardless of this initial reaction, because of these spectator ions involved and the salt that's formed, this net ionic equation holds true for any neutralization reaction. The slight caveat here is as long as the salt that gets formed is soluble. For example, an insoluble salt we know from prior in chapter 4 would be silver chloride. So as long as the salt is soluble, then this is going to be our net ionic equation for any neutralization reaction. We have the acidic hydronium ion, the basic hydroxide ions form neutral water molecules. Even though water can act as either an acid or a base, we usually see water present in its original form. That's because water is held together by very strong chemical bonds. We will come back to drawing these molecules. We'll get into drawing these molecules. This is what water looks like. So these bonds here are strong. That means that just spontaneously, we're not going to have water dissociate back into hydronium ions or hydroxide ions. The presence of these hydronium ions in solution is what makes a solution acidic. The presence of these hydroxide ions in solution is what makes a solution basic. Because water is a more stable form of these ions, actually a lot of energy is released when these ions combine together to form water. When a lot of energy is released, and we'll see this a lot more in our thermodynamics chapter, in chapter 6, when a lot of energy is released, this becomes an exothermic reaction. Or this can be described as an exothermic reaction. So where energy is released. That means it would take a lot of energy to break apart water into these respective ions again. So that's all why we have this forward direction arrow here. So these will form water, but the reverse reaction is very much not as likely to happen. So our final answer here is our acid, base, salt, and water. Everything is balanced. That was an important detail. Then also you can see example 4.4 in the main slide deck for more practice on these neutralization reactions. Now, for the next part in chapter 4a, we're going to get into redox reactions. In 4a part 2, we're going to just go over firstly, assigning oxidation numbers. Then in the remainder of 4a, we'll get more in depth with redox reactions. So for assigning oxidation numbers, we have some set rules we're going to follow and keep in mind, possibly write on our note card. Before we jump into the rules, let's first define the oxidation number. So the oxidation number is the charge the atom would have in a molecule or an ionic compound if electrons were completely transferred. We know, for example, that Na cation, if we had neutral sodium to start with and it became a cation, it must have released 1 electron to form Na+. This is the idea of an electron being transferred. So if we had a molecule or ionic compound like sodium chloride, then here we're asking about the oxidation number on sodium in the compound. meaning the oxidation number on sodium is the charge the atom would have if electrons were completely transferred. If Na has transferred one electron to chlorine for this to become Na plus and Cl minus, where Cl takes on another electron, the oxidation number of sodium in NaCl is +1. The oxidation number on Cl within this ionic compound is -1. So Na is +1, Cl is -1. So that's an introduction. Now let's go through these rules. So I mentioned very clearly that this is the oxidation number of sodium when it's within this ionic compound. Well, sometimes we have atoms that are not within compounds. Even these diatomic molecules, or even P4, so 4 phosphorus atoms altogether. When these are free elements that are uncombined or not combined with anything else, they have an oxidation number of 0. So just sodium on its own, oxidation number of 0. Just lead on its own, as a metal, for example, oxidation number of 0. Just oxygen gas on its own, each of the oxygen atoms has an oxidation number of 0. So that's rule number 1. If we have any free elements, always their oxidation number is just 0. Now for monatomic ions, we looked at sodium and chloride as an example. We can also look at other monatomic ions where the oxidation number in monatomic ions is equal to the charge on the ion. Lithium is an alkali metal. It forms +1 ions. Therefore, its oxidation number is +1. Iron can either be Fe2+ or Fe3+. If it's Fe3+, its oxidation number is +3. For Fe2+, its oxidation number is +2. These are all ions, right? So these are all charged. So an oxygen ion is very different than diatomic oxygen. Diatomic oxygen, no charge, no loss or gain of electrons. This is neutral oxygen with an oxidation number of 0. Oxygen, when it's become an anion, so it's gained 2 electrons. This oxide anion, based on its placement in the periodic table, will form 2- anions, meaning the oxidation number of oxygen within this monatomic ion is 2-. Rule number 3, the oxidation number of oxygen is usually -2. So recall oxygen's placement on the periodic table. The exception to keep in mind with oxygen is, of course, neutral oxygen or diatomic oxygen, where the oxidation number is 0. But for oxygen within an ionic compound or within a molecule, it's usually -2. The exception for oxygen, one of the exceptions is hydrogen peroxide and diatomic oxygen, but the anion form, where the oxidation number here is -1 and here is -1. Generally, we're not usually going to work with an ion like this, and hydrogen peroxide is an exception, so we're not normally going to think about the exception. Generally, we're going to think of oxygen having this oxidation number of -2, unless, of course, it's in a diatomic form where its oxidation number is 0. Next, the oxidation number of hydrogen is fairly predictable. So the oxidation number of hydrogen in an ionic compound or a molecule is +1. Except though when it's bonded to metals like group 1 and group 2 metals. So somewhat of an unusual compound is sodium hydride. It's fairly combustible, and here the oxidation number of hydrogen is -1. The oxidation number of sodium is +1. Generally, though, for hydrogen, we can associate its oxidation number as +1. Of course, though, also, aside from when it's diatomic hydrogen, where that oxidation number is 0. So hydrogen and oxygen are both pretty convenient to work with most times, where if we see hydrogen in a molecule or an ionic compound, it's usually +1, oxygen usually -2. Then continuing on in the pattern of what the elements prefer to form as far as cations or anions based on their placement in the periodic table, group 1A metals are +1, group 2A metals are +2, fluorine, a halogen, is always -1. These are also convenient, predictable cases. Next, I've been mentioning that the oxidation numbers within an ionic compound or a molecule, well, we can also think of the sum of all the oxidation numbers of all the atoms in a molecule or an ion is equal to the charge on the molecule or ion. We will do some examples using this rule. Next, oxidation numbers do not have to be integers, so the oxidation number of oxygen in a superoxide ion can actually be -1/2. Don't worry too much about these specific exceptions. Keep in mind just the general rules here, and we'll do some practice. So from this rule number 6 here, the sum of the oxidation numbers of all the atoms in a molecule or ion is equal to the charge on the molecule or ion. For example, with this polyatomic anion of carbonate, we know the formula here is CO3 2-. That means that carbon and oxygen, oxidation numbers on carbon and oxygen have to add up to 2-. Let's use our rules here. We know that oxygen is usually a -2 oxidation number. There are 3 of them. So -2 times 3, that is -6. Based on carbon's place on the periodic table, it prefers to form +4 ions. So we have 1 carbon, so +4 and -6 all add up to 2-. So we worked with a polyatomic ion here, carbonate. What about a neutral water molecule? Well, this should all add up to 0, right? Because this is not charged. So oxygen, usually -2, hydrogen, +1. There are 2 of them. So this is +2 and -2. This does sum up to 0. So either for a polyatomic ion, all of the oxidation numbers of the atoms have to add up to that charge, which also holds true for neutral molecules as well. Here, these all had to add up to 0. You could imagine a scenario then when you're given this total oxidation number and you have to figure out the oxidation number on just one of these atoms. Or you're given a formula and you have to figure out what that overall charge might be. So conveniently, there is this periodic table that can tell you generally which oxidation numbers each element will form. Importantly, the alkali metals +1, alkaline earth metals +2, silver just +1, like we saw with the ions that it prefers to form. Cadmium +2, zinc +2. Fluorine -1, carbon +4. So the ones in red are the more common ones that are listed. You can see that chlorine can actually form chlorine can actually have a whole variety of oxidation numbers. Just depends on the state of the atom and maybe what molecular ion it's in. Okay, so this will be another handy visual to have for these oxidation numbers. I've included this resource as well, so this is from Alex. So for example, OF2 minus, in red is fluorine, so the oxidation number of the highlighted atom is -1. Hydrogen, usually +1, oxygen, usually -2, and so on. This iodine is more interesting here. So in IF, its oxidation number is +1, but in IO3 minus, its oxidation number is +5. Let's look really quickly before going into that practice problem of why. So IO3 minus, each of the oxygens, -2. There are 3 of them, -6. For this whole ion to add up to -1 then, and we have -6 here, that means that iodine needs to be +5. +5 and -6 totals up to -1. Let's try this practice problem now. So here we have some species. We're going to assign the oxidation state of the highlighted atom in each ion or molecule. Remember, O2 is a molecule. It's not a compound because it only contains one element. Compounds have to be composed of 2 or more unique elements. So this is a compound. Here's a molecule or a diatomic species, so oxygen. Here's a cation, or just generally an ion. For some additional description on these oxidation numbers or oxidation states, the oxidation state of an atom when it's in a compound tells you how many more or how many fewer valence electrons the atom controls than when it's in its pure element or its neutral state. Atoms that are in a positive oxidation state have fewer valence electrons, right? So lose electrons or transfer electrons leads to a positive charge like we saw for the cations. Atoms with a negative oxidation number means they have more electrons. So if there's a transfer or a gain of negatively charged electrons, we're going to have a negative oxidation number, similar to what we saw for anions. Within this molecule of water, the oxygen is -2, the hydrogens are +1. That means that oxygen in water controls 2 more valence electrons than it would in its pure oxygen state. So for pure oxygen, its oxidation number is 0. Within water, its oxidation number is -2. That means oxygen in water controls 2 more negatively charged valence electrons than it would with pure oxygen. Similarly, for hydrogen, this is neutral. Then when in water, this oxidation number is +1. So for hydrogen atoms in water, they have an oxidation state of +1. That means a hydrogen atom in water controls 1 fewer valence electrons than it would in pure hydrogen. So 1 fewer valence electrons because it has that +1 oxidation number. We'll do a lot more on redox in the next part of chapter 4. We call redox reactions because we have reduction and oxidation. So redox, that's where that word comes from, redox reactions. In a redox reaction, the oxidation state of at least one atom must go up, and the oxidation state of at least one other atom must go down. So there's some transfer of electrons. There's some transfer of electrons in these redox reactions. Again, we'll look a lot more into this in the rest of chapter 4 or in the next part of chapter 4. But what will play into this is knowing how to assign oxidation numbers. We need to be able to assign oxidation numbers to see which atom has an oxidation number that goes up after the reaction, which atom has an oxidation number that goes down from the reaction. Okay, so we'll come back to this. For now, in our practice problem, we're going to assign the oxidation numbers of those highlighted atoms. Starting with Cu+, well, copper can form either +1 or +2 ions. Here it's evident that it formed a +1 ion. That means that this one is just +1. Copper is not involved in an ionic compound here, it's just an ion on its own, so that charge here is its oxidation state. Let's look at H3O+ now, which we definitely recognize as those hydronium ions. So H3O+, it all has to total up to +1, oxygen 2-, hydrogen +1. There are 3 of them, so that's +3 and -2. Does that total up to +1? Yes. So for the oxygen on its own, this is -2. Next, we're going to look at iron and sulfate. So SO4 2- and iron must be then Fe2+, just to practice more naming. This is iron 2 because iron can form +2 or +3 cations. So we have to include that Roman numeral there. This is iron 2 sulfate. Here we need the oxidation number of just sulfur. While we're on this page, for oxygen that is its own species that exists in its natural state, it's not bonded to anything, we know that oxygen here, both oxygen atoms will have an oxidation state of just 0. Right, that comes from this rule number 1 here. So these in its non-bonded or free element state have oxidation numbers of 0. So let's look at iron 2 sulfate now. And we just covered this one, oxidation state of 0. For iron 2 sulfate, it's really important that you recognize that sulfate is SO4 2-. That means the charge on iron has to be 2+ for this whole ionic compound to be neutral overall. Then oxygen, typically -2. There are 4 of them. So -2 and 4, that totals up to -8. +2 for the iron, right? Not +3. Then for sulfur, let's figure this one out. So this is +2, this is -8. This whole molecule though, or this whole ionic compound is neutral. So we have 2+ plus the charge on sulfur, which we'll figure out, plus -8 from the 4 oxygens has to total up to 0. So this is -6 and sulfur. That means that sulfur has to be +6 to make this total up to 0. So here's sulfur +6. Let me show you one other way that you can work this out. So I mentioned that SO4 has that charge of 2-. You have that memorized for sulfate. Let's just focus on SO4 2-. We know that has to total up to 2-. And then in this case, we wouldn't need to worry about the iron. So SO4 2-, oxygen still -2. There are 4 of them, so that's -8. So now we have the charge on sulfur and -8. This has to add up now to -2, right? So that's the charge on sulfate. This whole ionic compound was neutral, but here this has to add up to -2. That means sulfur has to have an oxidation state of +6. +6 plus -8 is -2. Here are our final answers then. Just for an ion is +1, oxygen -2, sulfur we figured out +6. then oxygen, just a free element, is 0. There is example 4.5 to look at for more practice in the main slide deck. It's going to be really crucial you're comfortable assigning oxidation numbers as we get into the rest in the next part of chapter 4. There we'll be working on actual redox reactions, so being able to identify these oxidation states will be important. I'm going to include this animation here on neutralization. Let me know if I can help with anything, and I hope you're all doing well, and I'll talk to you next time for more of chapter 4. I'm also including here some animations that are copyrighted and they are provided by the publisher.
Hydrochloric acid contains hydrogen ions and chloride ions in aqueous solution. Sodium hydroxide contains sodium ions and hydroxide ions in aqueous solution. When these two solutions combine, a neutralization reaction takes place. In this reaction, hydrogen ions from the acid and hydroxide ions from the base combine to form water molecules. The sodium and chloride ions are unaffected and remain to form a neutral sodium chloride solution. Neutralization can be summed up by this simple ionic equation.